perceive reality around you, you're doing so through a filter, and that filter is called a brain, and it's a very elegant, rather beautiful electrochemical filter with, for most of us, about 86 billion neurons, albeit maybe slightly fewer this morning. And each of those neurons, 86 billion neurons, has somewhere between 1,000 and 10,000 synapses. So it's almost, 100 trillion synapses. So it's an incredibly complex and very beautiful filter, but it's a filter. And so all that we know about reality is that which we can know through a human brain, which has a kind of a circularity to it. So in the late 1700s, Immanuel Kant came along and wrote many books. His kind of defining book was The Critique of Pure Reason. And in that, he conjectured, all right, so let's actually talk about phenomenal reality, is reality as we experience it through the electrochemical filter of a human brain, and then noumenal reality, which is reality as it really is. And that doesn't sound like a lot, but it broke with 1,000 years of empiricist tradition. I learnt about it at Oxford, where Locke, Berkeley, Hume, all the empiricists had gone to Oxford, so it was completely iconoclastic to even think that a German might have actually got it right. And it turns out the German got it right. And then fast forward from Kant about 150 years, I guess, to early last century, and quantum physics came along and so said, kind of right, because noumenal reality, as Kant would call it, it turns out that's very, very, very unlike phenomenal reality, reality as we experience it. And just a couple of ways, without delving too much into the depths, which can be quite discombobulating, of quantum physics, but the ways in which reality as it really is very different from reality as we experience it. One is that this notion of superposition. So we're used to a universe, and we call it determinist in the phenomenal reality, reality as we experience it, of things are either a 0 or a 1. But in noumenal reality, as Kant would call it, or coherent quantum reality, as the quantum physicist would call it, things can be a 0 or a 1 or any combination. That world, that realm, is described by these very beautiful wave functions. So they're probabilistic wave functions called Schrödinger wave functions. And they just describe the probabilities. Again, we can come back to any of this if it's helpful. And so that's a very unusual. Things can be a 0 or 1 or any combination. Something can be a wave or a particle or any combination. We're not used to that. That's not what we experience in the world in phenomenal reality as we experience it. And there was a NASA engineer called Hugh Everett in the late 1950s, and actually he died shortly thereafter of alcoholism and obesity. He was kind of run out of town. He was kind of ridiculed. He had a thesis called the many worlds hypothesis, or the many worlds interpretation, and was just roundly laughed out of town when he conjectured this. And it turns out it's almost certainly right. And the way to think about it, and I'll sort of articulate it, and then we can come back and unpick any aspect of it, is that noumenal reality, reality as it really is, or coherent quantum reality, as quantum physicists would call it, is a quantum entangled superposition of every possible configuration of the universe in a single instant, which takes some sort of getting used to. So it's a quantum entangled superposition of every possible configuration of the universe in a single instant. And actually, I should really say universe is... I'll come back to this. I should say actually metaverse rather than universe, because we now know that parallel universes exist. That was conjectured not that long ago. Now we know it to be true. So metaverse rather than universe. One aspect of that in a single instant is that a British, an Oxford philosopher and scientist called Julian Barber has written an amazing book called The Timeless Universe. And we assume, again, from our experience of phenomenal reality, that time is one of the dimensions of reality as it really is. It doesn't have to be. So any system needs what we call a relative configuration matrix in order for us to be able to locate something in it. And we're used to a relative configuration matrix that had 3 dimensions of space and 1 dimension of time. So in 6 weeks' time, we can roll back and say, oh, do you remember when Howard gave that amazing talk about client Earth, and we were sitting in a... So we can identify, when and where, and that's what we use for a very productive Cartesian relative configuration matrix. We take it, therefore, that time has to be part of any relative configuration matrix. It turns out it probably doesn't. So I'll just leave you with that, the notion that the universe is timeless, because that probably was not something that feels intuitive to us. I'll come back to any of that people want to explore in more detail, but I think it's helpful to have that a little bit of background before we talk about quantum computing. The thing to notice, the thing to state first actually about quantum computing is that quantum computers solve problems the way nature solves problems rather than the way humans solve problems. So, and a big theme of this conference is nature has the answers. And this is entirely, our approach with quantum computing is entirely aligned with that thesis. You could call it biomimicry. We often work with that term. And actually, Howard is still here. He talked a lot about AI and machine learning and the power of it. And we're big believers in that. And I think we're in... anybody who knows me knows I'm a yes and strategist. So yes, we're big believers in what we call human AI. So really, if you think about classical computing, it's built in our own likeness. It's a bunch of transistor gates. There are about 1 billion of them in your phone, and they can either be set to 0s or 1s. And when we talk about artificial intelligence, what we're technically talking about is artificial brackets human intelligence. It's intelligence artificially enhanced that is very much based on the human brain. And I think that's amazing in many ways. But in other ways that we've been talking about over the last couple of days, do we really want to take this that has caused so much trouble and artificially enhance it? I mean, I think along some dimensions we should pause on that thought. Nature AI, however, I'll come back to what we really mean about that, is solving problems the way nature solves problems. And it's fundamentally, it's a difference of kind, it's not a difference of degree. Before I get to that, look around you and you can see the kind of extraordinary problems that nature is serving all day, every day, in a very beautiful and elegant way. There is some pretty astonishing carbon capture going on around here. This young lady is just sort of all day, every day, taking carbon dioxide out of the air and turning it into oxygen. Pretty awesome. If you look at sources of energy around you, nature does a pretty good job with solar, with nuclear fusion, with electricity. And if you look around at the people have been talking this week about the soil, nature does an amazing job of fertilizer. Right? So the promise of quantum computing is that we can mimic and model these natural processes. So where are we now? Often in technology, it's probably helpful to talk about the stack, right? We talk about the bottom of the stack, the middle of the stack, and the top of the stack. So the bottom of the stack in quantum computing, the focus right now is on building qubits. So qubits are the quantum analog of a bit, a quantum bit. And they're a bit like bits that can be 0s or 1s, but with a couple of important differences. One is that they can be a 0 or 1, or anything in between, as we learned earlier. And every qubit is entangled, is associated in some way that I can explain later if we want more technicality, with every other qubit. And it's the combination of those two features that drive the superpowers of quantum computing. It's a kind of a big boys game at the moment, so Google, IBM, Microsoft, and various government, private entities in China are doing this. We, Elliot and I were at a Google Quantum Symposium last week in Santa Barbara, and we heard Google say it will take them about $3 billion from here to get to where they need to be over the next sort of 5-10 years. So this is a pretty capital-intensive thing. The quantum computers we have now, it's amazing that we have them. This was pure conjecture. The guy who runs um, the Google Quantum Lab is a very good friend of myself and Chloe and Elliot and Oswald and many others here, Dean, and luckily he is kind of one of us. He's been on lots of adventures with me in the middle of the Amazon jungle. He's been my Burning Man buddy for 20 years. He's a very, very unusual, very extraordinary individual who can reach for truth via quantum physics, and he can reach for truth via ayahuasca, contemplation, Lisa breathworks, and I think it's a very unusual combination when you can get an individual who can reach for the truth in both ways. So it should give all of us here great solace that an amazing human being like that is leading this effort. Google has, I used to work at Google. Google has built arguably, I'm probably not objective, but arguably the most powerful, quantum computer so far, and it's a tiny little baby one. It has 72 qubits in it. This, your phone has 1 billion bits in it, right? So we're in the foothills of all of this, and we haven't even figured out the best way to build qubits. There are different ways. Google uses superconducting. Other people use photonics. There's an approach called ion trap. There's some silicon approaches. So we haven't even really agreed on the way to build qubits, but we're kind of getting there. And we think that the journey, we need to be at a few hundred qubits before we can do really interesting stuff. But we were at no qubits only a year or so ago. So the fact that we're at 72 now and most of them entangled most of the time, we're almost in the zone where it can do really important stuff. And I'll come back to the stuff. In the middle of the stack, two important things going on. One is error correction. Qubits are very delicate creatures for reasons that you might expect after I've described how they're derived. Any quantum system, by the way, which quantum physicists would call coherent, decoheres the moment it is perceived. So as soon as a quantum state is perceived by a human or anything else, it decoheres into zeros and ones. So qubits are very delicate creatures. So one of the first orders of work is to build error correction. And we're not sure what the error correction overall needs to be in order to build the quantum optimization or quantum AI or nature AI as I described it earlier. We think that's still 5-10 years away, and it's probably something like 1,000 to 1. So in order to have 1,000 logical qubits doing work, we actually need 1 million physical qubits with 1,000 to 1 error correction, or something of that order. We don't really know. But in the meantime, the other thing that's happening in the middle of the stack is people are starting to build simulation platforms. I saw one in Palo Alto 10 days ago that blew my mind. So we're starting to be able to write software programs, simulations, on top of the hardware that's being built, even though the hardware is pretty embryonic and pretty non-error corrected. So we're at the point where the stack is getting built. And then if you move to the top of the stack, where the applications and algorithms, I didn't do that. That's not a Jedi mind trick. The applications and algorithms at the top of the stack, again, we heard this in Santa Barbara last week, and the Google Quantum Symposium is actually very open, and kind of almost every quantum company was there. It was actually pretty mind-blowing. And the likely expectation, the next 3 to 5 years is what we call NISQ, which is a noisy intermediate scale quantum computing era where we don't have a whole lot of error correction. We may have a few hundred qubits, but even with that, we will be able to do in the short term, there's something called quantum supremacy. So we'll be able to do a probability sampling better, faster, cheaper than the world's biggest supercomputer, which is called Summit at the moment. And when we say faster, we mean like 10 years faster. And so it's just a parlor trick on one level, but it's a pretty amazing parlor trick. So that's kind of the first thing that you'll hear about in terms of sort of applications and algorithms. The second, and I think it'll happen pretty soon, in fact, we know it's happening pretty soon, is something called quantum chemistry. And that gets back to being able to mimic and model what we see around us. there were a bunch of the automotive companies, I mean, you know, chairman of the big automotive companies at this symposium last week. They see this, one of the earliest applications is the understanding, doing a quantum chemistry simulation on top of one of these baby quantum computers to understand the process of replacing cobalt as the cathode for a lithium-ion battery, which is what we need. We've only got enough cobalt left for about 90 million batteries, even assuming like a 5-10x scale up and speed up in how efficiently we use cobalt. Cobalt, most of it is in the Congo. Dealing with warlords in the Congo to get cobalt is not something we want to do long term. And anyway, there isn't that much of this cobalt stuff, so we have to find something else. And running a quantum chemistry simulation is the way to do it. And quantum chemistry has existed, so quantum physics has existed over 100 years. Quantum chemistry has existed about 2 decades, but only in the classroom, because you can't run quantum chemistry simulations on classical architecture. You need a quantum machine to do it, even a baby quantum machine. So, you know, electric batteries probably, that should be one of the first things you see in every it's a public company, so I probably shouldn't talk about it too much, but you know, a lot of the car companies were there. The Department of Energy was there as well. We think there's really, really interesting stuff in not just electric batteries, but in solar, making much more efficient solar cells, and potentially in nuclear fusion too. I think you'll see some announcements around nuclear fusion later this year, and a lot of the innovation there is now happening because we can model it in quantum chemistry simulations. Bayer Monsanto and the fertilizer kings were in the room a week ago as well, and you know, I think we may have talked about it a little bit this weekend, but nitrogenase fertilizer, which is the only way we really know how to build fertilizer, takes 2 or 3% of the world's energy, and then nitrogen gets stuck in, you know, in the soil, and it's just all sorts of bad. So what we want to be able to do, and we think with even these baby quantum computers we can, is run quantum chemistry simulations of chemical processes that will allow specific fertilizer for this soil type, in this climate type, for this plant, with this amount of rainfall. So super, you know, focused. Same with drug discovery, super personalized drugs, because we can finally map the quantum chemistry processes that lead us there. So that's what we think is happening in the next 2-3 years. And then beyond that, quantum AI likely to be applied to complex logistical networks, maybe, you know, quant hedge fund trading. That is, in everybody's best guesstimate, something like 5 to 10 years away.